Welcome to another fabulous day in Calculus 3. And we're going to redo this example because the internet died last time. So take a look here. This is going to involve double integrals and volume. They gave us a capping surface, and that basically is the top of the solid right there. That's the equation for it. And the graph of it is a paraboloid that's opened upward, okay, with the vertex here at 1 on the z-axis. That's the ceiling of our room, if you will, of our solid. Now, the base of our solid is down here in the xy plane, but what does it look like? Because this solid doesn't cross through the xy plane like that other example we did. So we have to be given enough information to figure out what the base of the solid is. And they told us that the solid is located in the first octant, which means the base is located in the first quadrant here in the xy plane. So it's the base is somewhere here. And what's going on? So they gave us an equation, 2x plus y equals 2, which is the equation of a plane. So that's going to be one of the sides of the solid. But this plane does cut through the xy plane. And if you graph it, which I rewrote it where I solved it for y equals 2 minus 2x, and that's this little diagonal line right here. So the base of the solid is this little triangular sliver right here. And so if I graph this base here in my 3D coordinate system here, so there's the base of the solid. And that's going to be the region of integration when we set up our double integral. So this is the region R of integration, this base. Now, what does the solid actually look like? Well, if you use your imagination a little bit here, the base of the solid is this triangle, and then it kind of goes up, you know, there's sort of the sides of it. And then the upper, the capping surface, if you will, is curved. So this is sort of a picture of what the solid would look like. Kind of a weird looking solid here, but we're trying to find the volume of that. Okay, so the volume, if we use the definition in the theorem, is a double integral over the region where you put the capping surface in the integrand and then dA. dA could either be dy dx or dx dy. This is a generic double integral representing the volume. So now let's start filling in for the generic parts, okay? The capping surface was given. It was z equals x squared plus y squared plus 1. So there's that, okay? And then the dA, you get to pick which order of integration makes more sense, the vertically simple dy dx or the horizontally simple dx dy. I claim that this region right here could be either one, but I'm going to choose my personal favorite, dy dx. Yes, indeed. Now let's iterate the integral. That means we're going to put the limits on. Let's do the easy integral first, which is the outermost integral. Those limits always have to be constants. That is pure numbers. Not allowed to have variable outer integral limits. So what is x doing on this region? Well, look at the x-axis. It looks like it's swinging from 0 to 1. And that's exactly what you'll put for the limits on the integral. Now, what's y doing? Please do not look at the triangle and go, oh, it looks like y is going from 0 to 2. I'll just write down 0 to 2. No. Remember, all 4 limits, if they were all pure numbers, that would mean your region would look like a rectangle. And this triangle does not look like a rectangle. So you're not allowed to put 0 to 2 for your limits for y. So since we chose the vertically simple choice for the order of integration, we're going to draw a vertical little man inside of our region here. There he is. And his head is touching the upper limit for y, which has the equation y equals 2 minus 2x. So we'll put that down. And his feet are touching the lower limit for y, which is the x-axis, but that has the equation y equals 0. And there, we now have set up our double integral representing the volume for this lovely solid. So now let's go ahead and integrate. Okay, here we go. We're going to integrate with respect to y first, which means you hold x constant. So the antiderivative of x squared with respect to y is x squared y. The antiderivative of y squared with respect to y is y cubed over 3. And the antiderivative of 1 with respect to y is y. Now you evaluate between the limits. I'm going to continue to write the outermost integral down because it's still there. It hasn't disappeared. So now you're going to put your upper limit in there. You're going to substitute. So I have x squared 2 minus 2x plus 2 minus 2x cubed over 3 plus 2 minus 2x. And then minus 0, all of these terms will go to 0 when I substitute 0. So I'm just going to go ahead and skip that. That doesn't always happen. Be careful. Now, how do I integrate this? Well, very carefully. So if I had to integrate this by hand, and I do want to do this one by hand because I think it's important to show you some integration by hand, because some of us need a little bit of review for integration. So how would I integrate this mess by hand? Well, first I'm going to distribute this x squared. So I'll get 2x squared minus 2x cubed. And then I'm going to combine it with the plus 2 minus 2x. And then this term here, I am not going to multiply that out. I'm going to leave it. Okay, so what is my plan now? My plan is I'm going to integrate these terms, the first 4 terms, on a term-by-term basis, because those are just easy, terms to integrate from your days in Calculus 1. Okay. So this guy here is has an antiderivative of 2/3 x cubed minus this thing would be 2/4 x to the 4th, but 2/4 reduces to 1/2. Okay. Plus, then we have the antiderivative of 2 is 2x, and then we have minus x squared. Plus, now what about this last term? Let's just put an integral symbol in front of it because I'm going to show you how I'm going to deal with it. These guys, we will have to evaluate them between the limits of 0 and 1, but I'm going to hold off for now. I just want to look at this thing. Like how do we do it? Well, first, the 1/3 it's legal since it's a multiple there to pull it out in front of the integral. And then I'm going to use the power rule with u substitution. So I'm going to let u be 2 minus 2x. Then du is -2 dx. And then I need a -2. That's missing. I wish I had one. Well, I can make my dreams come true because I'm allowed to put a factor of -2 in here, provided I multiply the front of the integral by its reciprocal. Okay? Now, what do I have at this moment? Well, I have the number -1/6 multiplying the integral of u cubed du. So using u sub here, power rule, the antiderivative of u cubed is u to the 4th over 4, like that. And then you can multiply the 6 and the 4 together there, and then put your u back in. What the heck was it? Don't forget, it was that guy. Okay, now what I'm going to do is I'm going to call these guys all back. Hey guys, you can come back now. So I had the 2/3 x cubed minus the 1/2 x to the 4th plus the 2x minus the x squared, and then plus this last term. And I'm going to evaluate all of this between the limits of 0 and 1. Now remember, we're in the middle of evaluating a double integral that represents volume, so we need to get a positive result. That doesn't mean that every double integral in the world is going to give you a positive result. It won't. But if you're using a double integral to represent area or volume, you sure better get a positive result. Otherwise, something happened. That would be a red flag for you to look for your mistake. So when I plug 1 in everywhere, it looks like I just have 2/3 minus a half plus 2 minus 1 plus. And then this term here, when I plug in a 1, you'll notice it goes to 0, right? Minus, now look what happens when I plug 0 in for everything. Well, sure, I'll get 0 minus 0 plus 0 minus 0 plus, but this last term doesn't go to 0 when you substitute a 0. Be careful. Really see what I'm doing there. So what do I have here? So it's like, this is where I whip out a calculator and use my frac command. So first I go 2/3 minus a half plus the 1. I'll just frac that really quick. This ends up being 7/6. And then over here, I have a minus, which is going to affect the minus 1/24. So a minus minus is a plus 1/24. And then I'm doing the 2 to the 4th power. Oh, okay. So I get 7/6 plus 16/24. But I think 16/24 reduces, doesn't it? To 2/3. So now I have 7/6 plus 2/3, and then I'll use my frac command again, and I get 11/6 cubic units. So I'll put units cubed. And that is the volume of that strange looking solid. Okay? Okay. So we're going to look at example 13. And we have the capping surface fxy equals e to the negative y squared. They're also telling us that we're in the first octant. Please note, not all the problems will tell you this, because some of them aren't restricted to the first octant. Sometimes I'll tell students the first octant, and then they wrongly think or misinterpret my words, and they go, oh yeah, every single problem in the book is all going to be first octant. No, please do not assume that, ever. If they say the words first octant, then it's like, okay. And that means when you look at the base of the solid, it'll be in the first quadrant in the XY plane. But not all solids and not all the integrals we're going to do are relegated to the first octant. So be really careful that you don't assume that if that isn't implied. Okay. Now that means that the sides or the walls of this solid are going to be bounded by the coordinate planes, the XY plane on the bottom, the XZ plane, and the YZ plane are all going to be 3 sides to this weird looking solid. Okay. And in fact, there's going to be more. The vertical plane x equals 0, which actually is the YZ plane. Okay. Y equals 2x, that's another plane. And then the plane y equals 2. So there's a lot of boundaries to this solid. Now, I'm not going to sketch the whole solid, but let's think about what the region of integration would look like, which is essentially the base of the solid. So in the XY plane, we're going to graph some stuff, okay? And since they did tell us the first octant, that means that the base will for sure be in the first quadrant. Okay, that's good to know. Now what else? Well, we're going to graph x equals 0, y equals 2x, and y equals 2. Okay. X equals 0 is the vertical line on top of the y-axis. Y equals 2, is a horizontal line cutting through the y-axis at 2. And then y equals 2x is a diagonal line that cuts through the origin. So that's y equals 2x. Now, remember that my vegetable garden is bounded by all of these boundaries, these fences. So the base of the solid, I'm going to shade it in. You need to shade it in. If I ask you to do this on a quiz or an exam, that's the base of the solid. And this is the region of integration, region R of integration. So we're done with letter A. But before we do letter B, I wanted to take a look at what does the capping surface even look like? Because if I'm not going to ask you to draw stuff in 3D, but you know, it's a little bit harsh to ask somebody to draw something in 3D. But the base of the solid is right here, and then the capping surface is above here. But what does it look like? So let's take a look. See here at my graphing software. And I have fxy, but that's the same as z, equals e to the negative y squared power. And this is kind of a cool look. Whoa. Let me boost that look. That's kind of a cool looking capping surface, isn't it? Now remember, we're not considering this whole portion as our capping surface. We're only considering the portion in the first octant. Okay, so that's what the top of our solid looks like. Let's look at some other colors. Oh, pretty. Ooh. Oh, yeah, that looks pretty cool. I like that. That looks nice. Okay. So now you know what the top or the capping surface of our solid is looking like. Pretty cool, huh? So if you can imagine that look, if you will, sort of hovering over our base so that the solid would look, you know, something like that. Pretty weird looking. All right, so there's a solid. So now let's set up the double integral representing the solid. So we're like, hey, volume equals double double, and then you put your capping surface here, and then you can choose your order of integration. So, you know, I'm going to choose my personal favorite, dy dx, because, you know, I love that. And if I were to set up this double integral, dy dx, dx is the outermost integral. So what is x doing on this region? It looks like x is going as low as 0 and as big as a 1, so 0 to 1. Now, what is y doing? Please do not say 0 to 2. That is not correct. I put my vertical little man in there. There he is. Woo! Okay. Now the top of his head is touching this horizontal line, and that's the upper limit for y, but that has the equation y equals 2. Okay. So y equals 2 is our upper limit for y. Now his feet are touching the diagonal line. That's the lower limit. When his feet are touching is the lower limit. And that's the graph of the equation y equals 2x. Aha, so now we're done. We set up the double integral. Yay! Now it says, you know, evaluate the iterated integral. Let's go ahead and try to evaluate this. Now I'm saying try because you're going to see in a moment why this won't be integrable. So if you look at, I'm going to integrate e to the negative y squared with respect to y. Can't do it. This is not integrable. You can't use u sub or anything. It won't work because if you let u equal negative y squared, du would be negative 2y. And the problem with that is you don't have a y variable in there. And y is the variable of integration. And you're not allowed to put in a variable of integration in there. That's not legal mathematics. So you're stuck. Well, not really stuck. They did give you a hint. You may need to reverse the order of integration. And that's exactly what we need to do. Because I claim if we can reverse the order of integration and integrate dx dy instead, it will be integrable. Because then the dx will be the variable of integration for the inner integral. And the e to the negative y squared will be essentially constant. So let's switch. So you're still going to have your capping surface. That hasn't changed. It's still e to the negative y squared, but your order of integration will be dx dy instead. Okay, so let's iterate the double integrals. That is, put the little limits on the symbols. Let's do the outermost integral first because it's the easiest. You get pure numbers. And on this triangle, y goes as low as 0 and as high as a 2. You're only allowed pure numbers on the outermost integral. Now, what's x doing? Please don't say 0 to 1. That only works if your region of integration is a rectangle, and this isn't. So this is where it gets a little bit tricky. Because this is the horizontally simple choice for the order of integration, your little man needs to be positioned horizontal. In particular, you need his head to the right and his feet pointing to the left. Okay? Now, his feet are the lower limit for x, and that looks like his feet are on the y-axis, which has the equation x equals 0. So the lower limit for x is x equals 0. That was easy. Now the hard one. The guy's head is on this diagonal line, and that's as far to the right as he can get. So the upper limit for x is the diagonal line. However, it is illegal to put 2x here. Why is that not okay?
It would just be y over 2, right?
Yeah, but why is it not okay to put 2x?
You
Isn't
can't
it
have a
because it-
variable that you're integrating with respect to.
Good. It violates one of our rules. You can't have your limit of integration match the variable you're integrating with respect to. So instead, solve y equals 2x for x, which is pretty easy. Just divide both sides by 2. And then x equals y over 2 is going to be the upper limit for the x. Cool. All right, we iterated the integral. We're halfway there. Now let's go ahead and integrate. So now it's easy. It's totally integrable because when you integrate e to the negative y squared with respect to x, e to the negative y squared, this looks like a constant. So you're just going to get e to the negative y squared times x, and x is going to range between the limits of 0 and y over 2. Don't forget to put your upper limit first. I'll finish over here. So you'll still have the e to the negative y squared. So when you do, you're going to go y over 2 minus 0, but the minus 0 is like, okay, fine. So you're just going to have the y over 2. And now this, you're going to use the exponential rule. The exponential rule says the integral of e to the u du is e to the u. But first you got to tell me who the u is and who the du is. Now, before I do that, I'm going to rewrite this integral just because I don't like fractions. This 2 that's down in the denominator, you can pull it out front, which is really the multiple of a half. I'm just pulling out the half and having it multiply. Now let's do the u sub. So u is negative y squared, du is negative 2y dy. Good news and bad news. Good news, I already have a y dy in the integrand. The only thing that's missing is I need a negative 2. No problem. You can always put constants in there. So I'm going to put the missing negative 2 in there, provided I multiply the front of the integral by its reciprocal. Okay? The intermediate step that I want to see on your paper is what is it with respect to u now? It's negative 1/4 the integral of e to the u du, which is negative 1/4 e to the u. And then put your u back in before evaluating at the limits. A common student error is to go, oh, I'll just keep the e to the u and evaluate between 0 and 2. Well, then you're going to get the wrong answer. No, don't do that. You want to back substitute for your u. So my u is negative y squared, and that's what the limits are referring to. So now be careful because you're going to want to put the 0 in there because the 0 doesn't go to 0. This minus minus turns into a plus. Your final answer is kind of a weird number. It's negative 1/4 e to the negative 4 plus 1/4. That's the exact answer. And this is cubic units because we are talking about a volume. Now, is that a positive result? Like, does that look like it would be positive to you? Well, it turns out it is. I'm just evaluating on my calculator right now. The approximate answer looks like it's 0.245 cubic units. And that's a positive number. We'll go with that. Okay. So that's approximately 0.245. And that concludes that example. Example 14. I pulled this from another calculus book. It's kind of hard, but it makes a couple different points, which I like. So I included it in my lecture notes. So it's kind of tricky to visualize it though. That's one of the key weirdnesses about this weird problem. You've got a solid region that's bounded by what looks like a circle, but it's really a cylindrical surface. Remember, cylindrical surfaces are missing a variable and you have to whoosh it in the curve in the direction of the missing variable. So if I had to graph this cylindrical surface, I would first graph the generating curve, which is a circle centered at the origin of radius 3, and then I would whoosh it in the direction of the missing variable. So it would end up looking like that cylindrical surface right there. Excuse me, no, it's this one here. X squared plus y squared equals 9. So that's the first guy. Then the other solid that we're basically taking the intersection of two solids, and the intersection of the two solids is a solid, and that's the one we want to get the volume of. That's what makes this so weird. So the other cylindrical surface is y squared plus z squared equals 9. So if you graph the generating curve for that, and then whoosh it in the direction of the missing variable. The missing variable here looks like this is like the x. This is one of these GeoGebra problems, which is, they always get you turned around. So now the question is, what does the intersection look like? Like, oh my God, that's just nuts. It's hard to think about. So what I like to think about is, let's just consider that the solid is actually contained in all 8 octants. So it's like a kind of a big solid, but there is a lot of symmetry going on here. So how about if we figure out only what's going on in the first octant and then multiply that result by 8? So what I'm saying is the total volume will equal 8 times the volume in the first octant by symmetry. Now you can't always do this, but because the solid has a lot of symmetry, we can do it for this particular problem. You have to be very careful though when you claim you have symmetry, because I've seen students do that, and even if it might be correct, they're not even sure why. They're just guessing. So be careful. So what about the first octant? Like, what's going on? Well, in the first octant, if you look at your that wasn't very good. I gotta get the 3 here. This is if we look at only the first quadrant, this would be the base of the solid that's restricted to the first octant. Okay, and then the capping surface, well, we would have to rewrite the capping surface. We want to solve this for z, and when you take the square root of both sides, you'll get z equals plus or minus the square root of 9 minus y squared. And since we are in the first octant where z is always positive, we will have the positive square root of 9 minus y squared. Okay, so that's going to be our capping surface. All right, so now we're ready to set this whole thing up. So the total volume is going to be 8 times a double integral, where we're going to have a capping surface. So that's square root of 9 minus y squared. And I'm going to choose my favorite order of integration, dy dx. Woo! Sorry, I did not go my erase tool. Does weird things to the PDF. Ah, here we go. So if you look at this region of integration here, and you put the limits for x looks like it's going from 0 to 3. Okay. Then what's y doing? Be careful, don't say 0 to 3, because this region is definitely not a rectangular region. Put the little man in there vertically, like that. Okay. His feet are firmly planted on the x-axis, which has the equation y equals 0. Okay, that's good. Now his head is located on this circle, which had the equation x squared plus y squared equals 9. But if you solve for y, you get plus or minus the square root of 9 minus x squared, where the plus is the graph of the upper semicircle. And so we're going to take that, because that's where the little man's head is, y equals plus the square root of 9 minus x squared. Okay, we iterated the double integral. Now let's see if we can't do the integration. Big problem. I don't know if you see it, but this integral requires trig substitution. You guys remember trig substitution from your Calculus 2 course? And do you also remember it was no fun?
It was no fun at all.
Right. So I try to avoid any problems where I have to do trig sub in this class. So during a quiz or during an exam in my class, if you find you're in the middle of doing a trig sub question, stop yourself, take a deep breath, and start over. Because I never make you do that here. What do I do? What do I do? Switch the order of integration, and then you won't have to do trig sub. I don't want you to do trig sub. That's just totally not fun. So please. So what you'll do instead is you'll switch the order of integration, and then life will be good. That's the point. You don't want to be having a bad time. So what do I mean? So you're still going to have some things in place. You're still going to have 8. The capping surface is still square root of 9 minus y squared, but your order of integration will be dx dy instead. And hopefully this is all going to be wonderful when you work it out. Now, what are the limits? Don't, just guess. What is y doing on the base of our solid, which is this little piece here? Well, from a pure number to a pure number here, y looks like it's going from 0 to 3. You get pure numbers for your outermost integral. What's x doing? Now remember, dx dy is the horizontally simple choice for integration. So now when you put your little man in there, he has to be positioned sideways. Don't blow this, because if you're not getting this when you put your little man vertical and when you position him to the side or horizontally, you're not going to be doing so well for the next 6 weeks. Okay? And life will not be fun. You'll keep blowing these problems, and then you'll want to, you'll get so frustrated you want to quit. So little man's head is the upper limit for x. Little man's feet are the lower limit for x. So the little man's feet are the easiest, because that looks like it's flat, flush with the y-axis, which has the equation x equals 0. So that's the lower limit for x. But what about that upper limit? Oh man. Well, the upper limit is on the circle again. Oh, well, that's the square root of 9 minus x squared, right? No, it isn't, because square root of 9 minus x squared has an x in it. And we're in the middle of the integral that's integrating with the variable x. So that's not going to work. Well, what are you going to do? What are you going to do? Instead, you'll take the circle equation, which this is, and you'll solve it for x instead. And you'll get plus or minus the square root of 9 minus y squared. And if you graph the plus version, that's the right half semicircle. And if you graph x equals negative square root of 9 minus y squared, that'll give you the left-hand side of a circle. Well, our little man's head is on the right-hand side. So that means we'll take the positive x equals positive square root of 9 minus y squared for the upper limit for x. And now we're ready to integrate. And good news, we don't need any trig sub. Woo! Boy, we dodged a bullet there. That would have been terrible. Okay, integrate with respect to x, the square root of 9 minus y squared. Well, that's easy, because the square root of 9 minus y squared just looks like a constant with respect to x. So the antiderivative will be that constant times x, and x will range between the limits there of 0 and square root of 9 minus y squared. Don't forget, always plug in the upper limit first. That's what the fundamental theorem of calculus says we got to do. And so we'll plug that in and then plug in the lower limit, which is 0, and that's just 0, so I'm not going to bother. And then, hey, good news, people. When you multiply these two square roots together, what happens?
It takes away the square root.
We just get the radicand. And this is an easy peasy integral to integrate. It's just a little polynomial. And when we evaluate it between 0 and 3, I get 144 cubic units. And so that is the total volume of this weird solid. Okay. I hope that you're seeing, after a couple of examples that I just did, that having the skill of switching the order of integration is very, very important. This next example is sort of a double whammy in that it is not restricted to the first octant, but a lot of students, when I give a similar problem to this, they get it wrong because they wrongly think everything's first octant now. Be careful, because I always throw one in there, at least one, that isn't restricted to the first octant. Nowhere in the problem do they say first octant or anything like that. So be careful. You can't assume. So this solid is bounded by the graph of x plus z equals 2, and that's basically a plane. And then x minus y squared, which is a cylindrical surface. Okay, well, what the heck is that going to look like? Well, the capping surface is going to be, after I solve for z, z equals 2 minus x. That's the capping surface. Well, how do I know that? Because usually you try to pick your capping surface to be the fxy, and that's what z is. This other equation, which is a cylindrical surface, is going to help us determine the base of the solid in the xy plane. So if you rewrite it as x equals y squared, that is a horizontal parabola like that. And then the capping surface is just going to be like hovering above that in some way. I mean, if you wanted to draw this in 3D, you could. You'd have the base of your solid opening up in the positive x-axis like that. And then this capping surface so you see that plane, this portion of the plane that I drew? We only want the portion of the plane that's hovering over the base of our solid. We don't want the whole thing. So we only want to be restricted to, and I hope you can see that this plane that I drew does cut through the XY plane. You see that? And that's important because that's going to help cut off our base. A lot of times when students do this problem and they're not thinking, they go, oh, look, see, this parabola goes on forever and ever. It looks like the base of the solid goes on for infinity. They didn't give us enough information. We have an infinity base. No, 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 no. This particular solid's capping surface cuts through the x-axis. Well, where? If you want to see the trace, set z equal to 0 in this equation, and you'll get x equals 2, and that's what you're going to graph. That's the trace of the capping surface as it cuts through the xy plane here. And so the base of your solid is really just this little piece right there. It's just this right here. Okay. Now notice this base is straddling the first and the fourth quadrants. And it's definitely not going to be relegated to just the first octant. It kind of goes over a little bit. Okay, so don't assume. Not all regions are in the first octave. So we sketched the region of integration. This is part A, and this is the answer for part A. Now let's do part B. So you're going to set up a double integral. You're going to put the capping surface here in the integrand. I get z equals 2 minus x. You're going to pick your order of integration. Now, folks, I'm going to tell you a little secret. This region, you could either write it as dy dx or dx dy. You could treat it as vertically simple or horizontally simple. But because the parabola here is a function of y, the easier way will be the horizontally simple. It's going to be easier if you choose dx dy. Okay? For those of you that don't believe me, I'm going to set it up both ways and then we'll work it out. Okay? So let's just do dy dx, because I know a lot of people like, oh, well, why not? I'm going to do everything dy dx. You said it was your personal favorite. Well, yeah, I did, but not here. So here, what's x doing on this region? Well, it looks like it's going from 0 to 2. How bad could this be? Like my dad said, if you don't understand the answer, don't ask the question. Okay, so dy dx is vertically simple. Draw a vertical little man in here. Okay, this is where it gets weird. The man's feet are on the lower limit for y, which is that sideways parabola. But the man's head is also on the sideways parabola. Does that mean we put the same limit for y? No, 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 no. You wouldn't want to put x equals, you wouldn't want to put y squared here anyway, because you're not allowed to have the limits of integration match variable of integration. So what you're going to do is you're going to solve for y, and you're going to get that y can be plus or minus the square root of x. So I claim that the positive square root of x is the upper limit for y, and then this bottom part of the parabola is the graph of negative square root of x. And so there you go. And you can definitely integrate this integral. It's not hard, but you are going to have to integrate stuff that has square roots in it. So it gets a little bit messy. The easier way to set this volume up is to choose the horizontally simple choice for order of integration. And then y, now this one is a little bit weird, because what are the limits for y? What's the lowest and highest that y gets? It's not 2. The question is, what are the intersection points between x equals 2 and x equals y squared? Set x equal to x. When does y squared equal 2? Well, y is going to be plus or minus the square root of 2. So those intersection points have y coordinates of negative and positive square root of 2. I know, weird. And then what's x doing? Well, if you look at the horizontal little man, oh, it's getting really tough to draw this guy. It's sideways here. His head is on the upper limit, which is just x equals 2, and his feet are on the parabola, which is x equals y squared. Okay? And this is not hard to integrate. Either of these integrals are integrable. They're fine. You could do either one. So I'll let you do either one for practice. So I'm just going to say et cetera, et cetera. And if you did it right, both answers should be equivalent, and it should come out to be 32 square root of 2/15 cubic units. And that gives the result for that solids volume. And we're done. So I like this meme, although this isn't really a meme, because algebra, you'll notice, is a huge portion here. And I do find that sometimes Calculus 3 students run into some algebra silly mistakes that are a little bit strange. Okay.